Hi everybody, it's Miss Segovia and it's time to learn about lipids, which are your fats and your oils. So lipids we use for long-term energy storage and concentrated energy. Lipids are made out of carbon, hydrogen, and oxygen, except this time we have long hydrocarbon chains. We also have different family groups of our lipids. Our fats, like our triglycerides, our phospholipids, our steroids. Lipids do not form polymers like we saw in our carbohydrates. Lipids instead will form big molecules made of smaller subunits, no continuous chains. Lipids are basically, fats themselves are basically a glycerol, which is a 3-carbon molecule like you see here in the gray, carbon, 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 and then a fatty acid. Our fatty acids have chains of hydrogen and carbon. Whenever you see this type of molecule where it goes carbon, 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 each with a hydrogen sticking off the end, you're probably looking at a fat. Our head of each of those have an OH group here. It's actually a COOH, which is known as a carboxyl, and you'll learn a lot more about those in chemistry. Our fats come together just like our glucose molecules did with dehydration synthesis, where we take the hydroxide off of one side and the hydrogen off the other and form a water. And we remove it, which is why we call it dehydration. Little enzymes are there to help us along the way. One of the most common fats that you're going to see is the triglyceride. Our 3 fatty acids are linked to, right here, 3, 1, 2, 3, are linked to a glycerol molecule. These guys form what's called an ester linkage between the hydroxide and the carboxyl, and we get lots of water. And so when you see this for dehydration synthesis, you've got water, water, and water. Enzymes, again, help us each step of the way. These fats store lots of energy, and a lot of it has to do with their polarity. They are nonpolar, which makes them hydrophobic. Now, the reason they're great for energy storage is because they can concentrate that energy. It doesn't dissolve easily. And so we get twice as much energy out of them than we do our carbohydrates. We can also use them to cushion our organs and keep us nice and toasty like a whale, blah, blah. So why is it that we humans love fatty foods? Well, once upon a time we lived in caves and we did not get to eat that much. And so if we wanted to eat and store lots of energy, we craved fats. When we got those fats, we kept them in our body as long as we possibly could. Unfortunately, today we have easy access to fats, but our body still thinks we live in a cave. So we crave those easy access fats, and those fats stay on us, primarily hips and thighs. Yeah. Great. Our saturated fats are those that have all their carbons bonded to hydrogens, really, really stacked in there. And you'll see no double bonds, so we get these nice, long, straight chains. Since they're long and straight, they can stack up and stay solid at room temperature. Now, the bad thing here is our body loves to collect these, and it decides, hey, let's store it in your arteries. And so when we get lots of fat stored up in our arteries, we start to develop arteriosclerosis, and you get these plaque deposits. It's as though we stuck a whole bunch of boxes in the hallway and then told everybody to get through it just like they did before. Doesn't work very good. Unsaturated fats, on the other hand, have some double bonds to our carbons, which means that they're missing some of those hydrogen bonds. When we have those double bonds, we get these cool little kinks in there. And this makes us have it liquid at room temperature, like our plant and fish fats, veggie oils. They all stay kind of the liquidy, slimy, because the fat molecules can slide past one another and not get packed up really tightly like they could back in saturated fats. So when it comes to good versus bad, saturated fats are definitely bad for us. We don't want those because they can stick in our body and get built up along the sides of our arteries. Unsaturated fats, though, we're okay with those. They usually pass through our body pretty easily. We get some energy from them, but not nearly as much as we do from saturated. Another type of lipid that you guys are going to see and learn a lot more about are the phospholipids. These have a glycerol molecule with 2 fatty acids and a phosphate head. So we can see our glycerol down here and our phosphate up here. You'll recognize phosphate because there's a phosphorus atom in it. That phosphorus is negatively charged, and so that negative charge ends up having some cool little things to it. And so like our little guy here is telling us, it's like a penguin, it has a head. So we usually call this the phosphate head and the fatty acid tails. Now, why is that phosphate head really cool? Well, the fatty acid tails are hydrophobic. They hate water, while the phosphate head is hydrophilic and it loves water. And so one side is attracted to water, the other side is repelled by water. It makes it kind of like a split personality molecule, which ends up having some cool things. So where do we see our phospholipids? Well, we notice them in our cellular membranes. And so they allow those membranes to form, and if you just have a single membrane, you can form these really neat bubbles called micelles. But they can also form our phospholipid bilayer, which we find on every single cell in our body. And so it helps to form a barrier between the inside and the outside of the cell environment, because outside we have lots of water and inside we won't. And so we get these nice inside-outside definitions, really great cell membrane material. Soap, if we ever get soap on your membrane, soap goes in and it starts to destroy these bonds and make the cells fall apart, make it degrade, which makes it easier to clean. Steroids are another type of fatty lipids. These have 4 fused rings, a carbon, and then something else. That something else is this area up here on top, which we call a functional group. It's different in each type of steroid, but the bottom portion of the steroid stays relatively the same. And so different structure creates a different function for us. And so cholesterol and sex hormones are 2 of them that we'll learn a lot about this year. What you're looking at here is actually a cholesterol molecule. Cholesterol, you'll hear lots and lots of bad things about cholesterol, but it's actually kind of important for your cells in small amounts. And I'll show you that in a second. We also use cholesterol as a precursor to all other steroids, and again, I'll show you that too. Your sex hormones of estrogen and testosterone are actually made out of an original cholesterol molecule. Unfortunately, high levels in your blood may contribute to cardiovascular disease and cause lots of problems for you later in life. We use cholesterol in your cell membranes because we get those fatty acid tails here. Sometimes they can stack up and solidify, make your cell membrane kind of rigid, and we can't have that. We need your cell membrane to stay very fluid. And so those cholesterol molecules will go up there and kind of break it up and keep the whole system moving. Nice, fluid and flexible for our cell membranes, and allows transport of materials across and movement and lots of cool stuff you'll learn about later. With our sex hormones, if you look at them, you'll notice they all have the same basic ring structure in the center, but our little functional groups on the outside are all different. And so here you have cortisol and aldosterone, 2 steroids made from your adrenal glands. And then you have testosterone, estroidal, and progesterone, which are made in your gonads. So that's testicles for boys and ovaries for girls. If you look really closely at these, though, you'll notice very minor differences amongst them. So boys, you're not too far from being a girl. Girls, not too far from being a boy. Oh my goodness. So let's build you a lipid. We're going to do the triglyceride molecule. So we have a great big glycerol, 2 saturated fatty acids, and we know that they're saturated because every single carbon that you see on here has a hydrogen bonded to it. Now if you look down here, we've got a double bond with our carbon and we're missing 2 hydrogens. That tells us that this is an unsaturated fatty acid. This is very important that you recognize the differences between these 2, because I'm going to test you on it. Now if you look at your glycerol, you'll see our hydroxide groups here, and on our fatty acids you see them as well. When we bond those, we'll take the hydroxide off of one and the hydrogens off the other and have our little water droplets. So you guys go ahead and cut them out, put them onto your water droplets, and attach that into your notebook. This should go kind of in the center of page 10 like you see in the picture. And that is how we do our lipids.